Dehydration reactions. These are your classic E1 reactions. And what dehydration reactions is, as the name implies, you're formally losing a water molecule. All right. So what if on an exam you were given this and it may ask you to draw a plausible mechanism for this reaction? How would you do it? Well, let's start. All right. So draw an organic substrate. All right. The first thing that is going to happen, and again, it is helpful to think of any sort of whether it's phosphoric acid, sulfuric acid inside a strong acid. Right, maybe you should add this in heat as some sort of H plus in solution. Right. So in the first step of the mechanism, what is going to occur in a classic dehydration E1 reaction? You're going to have protonation. So these electrons off the oxygen on the organic substrate is going to come and grab a hydrogen. And the reason for this is because hydroxide is a terrible leaving group. It's not a great leaving group. And so it has to form water to get water as a leaving group, which is much more better. So you will have you arrive at an intermediate that looks like this. Now you would have hydrogen and oxygen with a plus charge, this methyl group here. All right, now you arrive at something like this. And now simply in the next step of the reaction, these electrons pops off on the oxygen, to give water, which is a great leaving group. All right, and now we have a form of plus one charge on this. We have a form of plus one charge on this carbon here. And simply that same water molecule that left will just comes in now and act as a nucleophile and bond to this. Well, wrong. Not act as a nucleophile because we're going to form the same thing, but it's going to act as a base instead. So this error is wrong. So it's going to act as a base instead. Getting ahead of myself here. Takes all these hydrogen and kicks off to satisfy that plus charge there, and we arrive at a neutral product that may look something like this. And that will be a plausible mechanism for this reaction here. So dehydration reaction is formally you're losing a water molecule you're losing a water molecule to form an alkene, right? And there you could see, right, we have OH, we have two hydrogens here, but look at our product, right? The OH is gone, and now we have one hydrogen here, right? So there's our H2O that we lost. So let's look at a couple more examples. What if you're given this molecule and you decide to add hydrochloric acid to it? What will happen? Well, again, in the first step of the mechanism, protonation occurs, right? And maybe you could also think of HCl. Could also think of HCl as some sort of H plus in solution. All right. So the first thing that occurs is protonation. So these electrons or oxygens come and grab a hydrogen. And we arrive at something like this in the mechanism. We have an oxygen with two hydrogens and plus one formal charge. These electrons kicks off on the oxygen, and now you arrive to something that looks like this. You're gonna have a plus one formal charge on that carbon there. Now, notice that my carbon here is secondary. I have a tertiary. I could make this molecule more stable by doing a 1-2 hydride shift, right? By having my plus charge on a tertiary carbocation, right? So these hydrogens are going to come and satisfy that plus charge there. We should do 1-2 hydride shift. And now we're going to arrive at an intermediate that looks something like this. Now my plus charge is going to be on this carbon here, which looks much more better, right? So in the next step of the mechanism, water comes in and acts as a base, right? Kicks off these hydrogen, takes all these hydrogen here. These hydrogen kicks off to form the carbon-carbon double bond, right? So we arrive at a product that may look something like this, right? And this will be a Zaitsev product. All right. Now, bear in mind that to get our Hoffman product, plus charge here, this H2O, this water molecule here, could also come in, take off one of these hydrogens here. All right, kicks off on the car, takes one of these hydrogen here and kicks off the electrons there to form that carbon-carbon double bond, and we may arrive at a product, something that looks like this. And this will be your Hoffman product. But this will be a major product you'll most likely see. Now, remember we talked about the Zaitsev versus the Hoffman product. Usually, your Zaitsev product will always be the more it is always the more substituted and more stable product. And usually, a Hoffman product will be the double bond will be somewhere at the end, right? So you could think of this double bond as being kind of, see how many carbons it's connected to. 1, 2, right? So this is di-substituted. Here, this double bond is connected to 1, 2, 3. So this is tri-substituted, right? So let's look at another example. What if you're going to lab and you run this reaction with T-amyl alcohol, right? And you added hydrochloric acid. Well, again, what would be the product? E1 reaction, classic dehydration reaction, a hydroxide turboleaving group. So therefore, you have to have some sort of protonation, right? So thinking of hydrochloric acid, that is just the same thing as some H plus source in solution. Right? So in the first step of the mechanism, these electrons come and protonate, or protonation, right? So now you arrive at something that looks like this, an oxygen with 2 hydrogens and a +1 formal charge, right? Now these electrons kicks off on the oxygen, and now there we have our leaving group. But there's no rearrangement needed in this reaction because, again, we already have our plus charge on a tertiary carbocation. All right. So the last step of the mechanism, water now comes in, act as a base. All right. To get our Zaitsev product, comes in the base, takes out these hydrogen, kicks out these electrons here, and we arrive at a neutral product that may look something like this. Product that may look something like this, forming an alkene.